Humans use more concrete than everything else we build with combined. After water, it is the most consumed substance on the planet. We pour enough of it every year to bury a city, and almost nobody knows what is actually in it or the strange chemical trick that makes it work. The first thing to clear up is that concrete and cement are not the same thing, and mixing up the words hides how the whole material works. Cement is just the glue, concrete is the finished stone. A typical mix is only about 10 to 15% cement. Most of the volume, 60 to 75%, is aggregate plain rock. Crushed stone and gravel for the big lumps, sand to fill the gaps between them. The rest is water, so concrete is really just rock and sand glued together by a thin paste of cement and water. And that is the key idea. The rock is doing most of the structural work. The cement paste only has to coat every stone and lock the whole mass together into one solid piece. The clever and dirty part is the cement. It starts as limestone dug out of quarries by the million tons. The limestone is crushed, blended with a little clay, and fed into an enormous rotating kiln, a steel tube longer than a football pitch, tilted slightly and lined with firebrick. Inside, it is heated to around 1,450 degrees Celsius, hot enough to chemically break the rock apart. What comes out the far end are hard gray nodules called clinker. That clinker is then ground to an extremely fine gray powder, and that powder is cement. There is a catch that matters. Making cement releases enormous amounts of carbon dioxide, both from burning fuel to reach that heat and from the limestone itself, which gives off CO2 as it transforms. Cement production alone is responsible for around 8% of all human carbon emissions, which is why so much research is going into cleaner ways to make it. Here is the part almost everyone gets wrong. Concrete does not dry out to get hard. If it simply dried, it would be weak and crumbly. What actually happens is a chemical reaction called hydration. The moment you add water to cement, the cement grains start to dissolve and react with the water, growing tiny interlocking crystals that reach out and knit the whole mixture together from the inside. It is the water that makes it hard, not the loss of it. This is why concrete can set and cure perfectly well underwater, and why fresh concrete is kept damp, not left to dry in the sun. Let it dry out too fast and the reaction stops before it finishes, leaving weak, dusty concrete. That reaction is also why concrete keeps getting stronger for weeks. It reaches about 90% of its strength in the first 28 days, which is why 28 days is the number engineers test against all over the world. But it carries on hardening very slowly for years. Concrete has a split personality, and understanding it explains almost every piece of steel you have ever seen buried in it. Concrete is phenomenally strong in compression. Squeeze it, push down on it, pile weight on top of it, and it will carry an enormous load, which is why it is perfect for the columns and foundations holding a building up. But pull it apart, bend it, stretch it, and it is pathetically weak. It cracks and snaps with very little warning. A concrete beam left plain would break the instant you loaded the middle of it because the bottom face gets stretched. The fix is to cast steel bars reinforcement into the parts that will be stretched. The concrete handles the squeezing, the steel handles the pulling, and the two together reinforced concrete is one of the most useful structural materials ever invented. It is also a happy accident of physics that steel and concrete expand and contract at almost exactly the same rate when the temperature changes. So they stay bonded together through heat and cold instead of tearing apart. So why did concrete beat everything else and end up as roughly 70% of all the material humanity produces every single year? It comes down to a handful of unbeatable advantages. It is cheap because its main ingredients, rock, sand, and limestone, are some of the most abundant materials on Earth and are found almost everywhere, so you do not have to ship it far. It is moldable. You pour it as a liquid and it takes the exact shape of whatever form you build around it, so the same material becomes a dam, a bridge, a pipe, or a floor. It is durable and tough. It does not rust, rot, or burn, and it stands up to water, wind, and fire in a way timber and steel alone cannot. And it is heavy and dense, which makes it fireproof, soundproof, and gives buildings thermal mass that smooths out the temperature swings inside. Cheap, strong, shapeable, and available literally everywhere. Nothing else ticks all four boxes at that scale. For all that, concrete is not perfect, and its problems are exactly why it is one of the most active areas of research in construction. The carbon cost is the big one, that 8% of global emissions, and engineers are attacking it from every direction, blending cement with waste products like fly ash and slag to use less of it, developing entirely new low-carbon cements, and even injecting captured CO2 back into the mix so the concrete traps it permanently. Then there is durability. Reinforced concrete has a hidden weakness, because if water and salt reach the steel inside, it rusts, and rusting steel swells and cracks the concrete open from within, which is why so many mid-century bridges and car parks are crumbling today. The answers being worked on are remarkable, from stainless and coated reinforcement to self-healing concrete laced with bacteria or capsules that seal their own cracks. The most ordinary material in the world, the gray stuff we walk past without a glance, is quietly one of the most advanced. And the fundamental recipe, rock and sand glued with a paste that hardens by chemistry rather than drying, has not really changed since the Romans. We have just spent 2,000 years learning how to use it. Follow for more construction facts hiding in plain sight.